Hey everyone, let's jump straight into it. Today, we're decoding Cambridge IGCSE Math probability. And honestly, this is one of my absolute favorite topics. We're going on a bit of a journey, starting from the absolute basics. You know, those simple single events. And we're going to build all the way up to mastering complex, multi-layered tree diagrams. So whether you're strictly prepping for your exams to extract maximum marks, or you just kind of want to understand how to map out the mathematical odds of the universe, you are in exactly the right place. Let's get started.
Okay, here's our roadmap for today. First up, the foundation. Then we'll tackle the 2D challenge. And finally, we'll conquer the branching path.
Section 1. The foundation.
All right, to kick things off, we really need to understand that probability is simply how we measure the likelihood of an event happening. And the absolute golden rule here, the probability scale strictly exists between 0 and 1. There is no wiggling out of this one. You can write it as a fraction, a decimal, or a percentage, but it literally cannot escape those bounds. 0 means something is utterly mathematically impossible. No way it's happening. 1 means it's an absolute certainty. So if you think about a perfectly fair coin toss landing on tails, well, that sits right smack in the middle at 1/2, or 50%.
But how do we actually land on those exact numbers? Well, we basically use two different approaches. First, there's theoretical probability. This is what we use when we already know all the possible outcomes. Think of rolling a standard six-sided dice. We know the physical limits of the dice, right? So we can just calculate the odds theoretically. On the flip side, we've got relative frequency. We use this for estimated probability, like, say, trying to guess the likelihood that you'll play sports tomorrow. That totally varies from person to person. We can't mathematically calculate that from a physical object, so instead we have to estimate it based on past data and frequency.
Let's put this into practice and see how theoretical probability applies to some actual data. Take a look at this table. We've got 30 students, broken down by boys and girls, along with their favorite subjects. Having data organized in a table like this makes calculating single events an absolute breeze. For instance, if I ask you, what's the probability that a randomly chosen student is a girl? Well, we just check our totals. We have 16 girls out of 30 students total. So our probability is simply the fraction 16 over 30. Simplify that down and you get 8 over 15. Super easy, right?
But let's be real, life rarely throws just one single event at us at a time. So here is the million-dollar question. What actually happens to our math when we toss 2 coins instead of 1? Or if we roll 2 dice? How does the whole mathematical picture change when a simple single event turns into a combined event?
And that brings us to Section 2, the 2D challenge.
So, when 2 independent events happen at the exact same time, we really need a visual tool to keep our calculations nice and organized. Enter the sample space diagram. What we're looking at right here is a map of rolling 2 fair six-sided dice. By putting dice 1 on the vertical axis and dice 2 on the horizontal axis, we create this really neat two-dimensional grid. And this grid brilliantly maps out all 36 possible combinations. If you want to find the probability of, say, rolling double 3s, you literally just pinpoint that single intersection on the grid. Boom, right there, it's 1 out of 36. It's a hugely powerful visual aid.
But, yeah, there's a catch. Sample space diagrams have one major glaring limitation. They only work for exactly 2 combined events. The very second you introduce a third event, like rolling 3 dice or spinning a coin 3 times, this 2D grid becomes completely useless. I mean, we don't exactly have 3D paper to draw a mathematical cube in the exam hall, right? So our visual tool just completely breaks down.
Which is exactly why we need to level up to Section 3, the branching path.
Let me introduce you to the ultimate hero for 3 or more events, tree diagrams. Let's methodically walk through exactly how to construct one, using the example of spinning a standard coin 3 times in a row. It's actually a very simple 3-step process. Step 1. Draw the branches. You start at a single point, then draw a branch for each possible outcome of your first spin, heads and tails. From the ends of those, you draw fresh branches for the second spin, and so on. Step 2. Write the probabilities right beside the branches. For a coin, obviously that's 1/2 on every single branch. And finally, Step 3. Write your final combined outcomes at the very ends of the branches.
Now check this out. By following those branches from left to right, we end up with this beautiful, comprehensive list. These are the 8 distinct outcomes for spinning a coin 3 times. It tracks every single possibility flawlessly, from getting 3 heads in a row at the top, all the way down to 3 tails in a row at the bottom. It basically guarantees that you won't miss a single combination, no matter how chaotic the problem might seem at first.
Okay, so how do we actually use this thing to get our answers?
Well, there is a golden rule for tree diagrams, and it all comes down to knowing when to multiply versus when to add. Here's how it works. You multiply the fractions as you travel along the branches from left to right to reach one specific final outcome. But, and this is absolutely crucial, if a question asks for a scenario with multiple successful outcomes, like getting at least 2 heads, you find those individual probabilities first, and then you add those final outcomes together. So just remember, multiply across, add down.
Let's actually put that multiplication rule into action. What's the probability of getting exactly 3 heads? Well, we trace that top branch. Heads, then heads, then heads. That's 1/2 times 1/2 times 1/2. You multiply the numerators, multiply the denominators, and bam, you get 1/8. It's super visual, incredibly intuitive, and mathematically rock solid.
Now, so far, we've only been talking about coins and dice, which are, perfectly fair. But let's think about the real world for a second. What if the outcomes are not equally likely? What happens to our perfectly balanced diagram when the probabilities aren't just a neat 50-50 split?
Honestly, this is where the true power of the tree diagram really shines. Unlike simple fractions, the branches on a tree diagram can hold absolutely any probability fraction you throw at them. Take this real-world example from our source material, a netball team playing 3 matches. They can win, lose, or draw. Now, those outcomes are almost definitely not equally likely. A team might have a really high probability of winning and a super low probability of drawing. But the tree diagram, it doesn't care. You just write those specific, unequal fractions on their respective branches. And that multiply across, add down rule, it works exactly the same way. It maps out totally realistic, unbalanced scenarios without breaking a sweat.
Which brings us perfectly to this quote from our foundational source text. When more than 2 combined events are being considered, tree diagrams are a good way of doing this. Honestly, I think that's a bit of an understatement. They aren't just a good way, they are literally the ultimate way to bring order to mathematical chaos. So, my final question to you is this. Beyond just snagging top marks on your math exams, where else in your life are you facing a complex series of choices? How could you use the branching logic of a tree diagram to map out your own decisions and calculate the probabilities of your own success? It's definitely something to think about. Thanks so much for joining me today, and keep calculating those odds.